Welcome, calculus students. This lesson is on polar coordinates and curves. Plot the following points given in polar coordinates. Now this second number represents an angle, and this first coordinate we'll call r, which will stand for the distance the point needs to be from the origin. So we have this spider web looking grid with different angles and a series of concentric circles. So we rotate 30 degrees counterclockwise, and then along that trajectory, we place a point that's 2 units away from the origin. So here's a half, here's 1, here's 1.5, and here's 2, is indicated by this number. And our point is right here. Now the indications that we're looking at a point using polar coordinates, we have the obvious clue here. We also have the clue that the second number represents an angle because of this degree symbol. And I also like to use these square brackets instead of parentheses to indicate that we're talking about a polar coordinate system. Now let's focus on point B. So we're going to rotate negative 45 degrees and then go a distance of 2.5 units away from the origin. The negative rotation means rotate clockwise 45 degrees from the positive x-axis, and then we place the point 2.5 units away from the origin, which will be located right there. Point C will rotate counterclockwise 300 degrees, here's 90 degrees, 180 degrees, 270 degrees, and 30 degrees more. But the fact that we have a negative value for r, negative 1 in this case, indicates that we should go 1 unit away from the origin, but along a trajectory that's opposite the direction of 300 degrees. So if you extend that ray into the second quadrant, we would place our point 1 unit away from the origin, but in that direction, putting point C right here. Now for point D, this angle is measured in radians. Notice there's no degree symbol. It's positive, so we rotate counterclockwise 7 pi 6 radians, putting us into the third quadrant, and then we place our point 3 units away from the origin in that same direction, putting point D here. For point E, we will rotate negative 3 pi halves, so that's clockwise 3 pi halves. That rotation winds up giving us a ray pointing straight up. Then we focus on the r, which is negative 4, which means we should go 4 units away from the origin, but in the opposite direction of negative 3 pi halves. That puts point E down here. Point F, we rotate 7 pi counterclockwise, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and 7 pi. And then we go a radius of 1.5 units in that direction, putting point F right here. Point G, we rotate negative 2 pi, which is just 1 full rotation around the circle clockwise. But then we go a distance of 0 units away from the origin. So point G is actually just at the origin. In fact, if r is 0, then it won't matter what theta is, indicating the possibility that there may be more than one way to express a location in polar coordinates. Now look at the coordinates of point H. This time the pi is here and the 1 is here. This might make you want to default to the first number being the angle and the second number being our r value. But unless you're told to do that reversal, you must assume that the first number is r and the second number is theta. Notice that there's no degree symbol, so we should interpret this 1 not as 1 degree, but as 1 radian. Let's convert this to degrees. Multiply by the converting factor. 180 degrees corresponds to pi radians, which gives us about 57.3 degrees. So this point, pi is about 3.14, and 1 radian is about 57 degrees. So to plot this point, we focus on that angle first. Well, pi thirds is 60 degrees, so we're a little bit less than that. And then we go 3.14 approximately units away from the origin. Well, here's the 3 mark, so go a little bit past that, and we have point H. All right, let's go on to the next page. This page focuses on converting between Cartesian and polar coordinates. To describe a point somewhere in the xy plane, the Cartesian coordinates would be to use an x-coordinate to know how far to the right or left of the origin we go, followed by a y-coordinate, which gives us the vertical displacement to find that point. So in rectangular or Cartesian coordinates, this point is described by xy in parentheses. But we've also just reviewed that I can describe this location by rotating theta degrees and then going a distance r from the origin. So in polar coordinates, it would be bracket r comma theta. Also notice that when talking about polar coordinates, sometimes the origin is referred to as the pole. So we want to learn how to convert between these systems. If you know the polar coordinates are theta, how do you find the rectangular coordinates xy? And then similarly, if you know the xy coordinates, how would you go about finding the polar coordinates? Some relationships that are obvious in this image is that we are looking at a right triangle, so we can apply the Pythagorean theorem to relate x, y, and r. Also, we can use trigonometry. We know that the tangent of this angle will be the opposite, which is the y-coordinate, divided by the adjacent, which is the x-coordinate. Another relationship I see is between theta, x, and r. We know that the cosine of theta is equal to the adjacent x divided by the hypotenuse r. And then relating y, r, and theta is the sine function. We know the sine of theta is opposite y divided by hypotenuse r. These four equations give us the foundation for doing the two conversions we are seeking. So if you want to convert from polar to rectangular, we use these two equations. Multiply the r's to the other side, and that gives us that x can be found by doing r cosine theta, and y can be found by doing r sine theta. So if you know r and theta, you do these two calculations to find x and y. Now to convert the other way around, if you know the rectangular and you want to find the polar, you will use these two equations. So r can be found by doing the square root of x squared plus y squared, and you could keep the plus or the minus value. We're going to see that you will have options. And then to find theta, we're going to have to solve this equation using adjustments of the arctangent of y over x, depending on the quadrant that we're after. The simple direction will be polar to rectangular, and the more complicated direction will be going from rectangular to polar, because we're going to see that there are infinitely many ways you can write the location of a point using polar coordinates. Let's put this to practice on the next slide. Express the given polar point in two other polar forms. Then convert these points in polar coordinates to rectangular or Cartesian coordinates. So let's rotate an angle of 15 degrees. Pi 6 is 30 degrees. So this ray right here is our 15 degree ray. And then we have a negative r value, placing our point 3 units away from the origin, but in the opposite direction of 15 degrees. Now this location can be described in many ways using polar coordinates. Instead of rotating counterclockwise 15 degrees, I could have rotated clockwise 165 degrees, and then used a positive value of 3 to describe the same location. So positive 3 for r and a negative 165 degrees for theta. Or we can also rotate clockwise until we have a coterminal angle with 15 degrees. That would be negative 345 degrees, which points into the first quadrant, but then use a negative 3 for r to wind up in the third quadrant. So another way is to say negative 3 for r and rotate clockwise 345 degrees. Another option is to rotate counterclockwise in standard position until we are in the third quadrant as appropriate. This would be a rotation of 195 degrees. And because 195 degrees already points into the third quadrant, we would use a positive 3 for r, giving us the polar coordinates 3, 195 degrees. Now we could keep this up forever, suggesting that every point can be described in polar coordinates in infinitely many different ways. However, a point in the xy plane will have a unique representation if you use rectangular or Cartesian coordinates. Now we will convert to rectangular. So we want to find the xy coordinates of this location, where x would be how far left we go from the origin and y would be how far down we go from the axis. So we will use these two. And the nice thing about these formulas is it doesn't matter which polar coordinates you use. So you can use this point, or this point, or this point, or this point. Let's do two of them. So using 3 for r and 195 degrees for theta, we get that x is equal to 3 cosine of 195 degrees. Type that into Desmos. Make sure you are in degree mode. And we get a result of negative 2.898 with some rounding. And the y-coordinate will be 3 sine of 195 degrees, giving us about negative 0.776. Notice both coordinates are negative, which is to be expected for a point in the third quadrant. We could repeat this using negative 3 for r and negative 345 degrees for theta. Typing those into Desmos, and you see we get the exact same xy coordinates. Okay, moving to the next page. Now converting from Cartesian to polar is a little bit trickier. Our point in rectangular is negative 3, 2, so go left 3 and up 2. That puts us right here in the second quadrant. So the most simplistic approach is to determine what r is, which will be the distance between this point and the origin. And let's assume a positive value of r in this drawing. Now I want to find the angle in standard position that would rotate us correctly into the second quadrant. And because we're rotating counterclockwise, this theta will also be positive. So we'll begin by looking for these two values. Theta should be somewhere between 90 and 180 degrees, and r should be positive. Well, our tools are the Pythagorean theorem, because we know that r is the hypotenuse of a right triangle, whose height is 2, and whose base has a length of 3. So Pythagorean theorem was that x squared plus y squared should be r squared. And it doesn't matter if you think of x and y as positive or negative, because when you square them, the result will be positive anyway. But technically, the x-coordinate is negative 3, and the y-coordinate is positive 2. So we get 9 plus 4, we get 13, and then take the square root. So r could be plus or minus the square root of 13, and we're going to assume the positive version for our first way to describe this point. Now let's try to find theta. We know that whatever theta is, the tangent of theta will be equal to the y-coordinate divided by the x-coordinate. So in this case, it'll be negative 2/3. Here, it does matter that you use the correct positive or negative value for x and y. So if I calculate the arctangent of negative 2/3 in an effort to find theta, do this using technology. So I type in arctan and then negative 2/3, and we are still in degree mode. So this gives us negative 33.69, which we'll just round to negative 33.7. And that's measured in degrees. You can see very obviously that this is not the angle that we are looking for, but it is related to the angle that we are looking for. Negative 33.7 degrees rotates into the fourth quadrant and gives us a ray that's an extension of the other ray that extended into the second quadrant. And it is still true that if you were to draw a right triangle here, you would have a positive 3x coordinate, a negative 2y coordinate, and the tangent would still be negative 2/3. Keep in mind that when you use an arctangent, you can only get angles between negative 90 and 0, so in the fourth quadrant, or between 0 and 90, so the first quadrant. The arctangent cannot produce automatically an angle that's in the second or third quadrant. So we have to adjust this answer to find our theta. So the theta in our drawing we would find by adding a counterclockwise half rotation to the arctangent of negative 2/3, giving us approximately 146.3 degrees. So one answer that we're looking for our theta could be rotate 146.3 degrees, which puts us into the second quadrant, and then go out positive radical 13. Now we're supposed to give two answers where theta is between 0 and 2 pi. From angle theta, if you rotate another 180 degrees counterclockwise, gives us an angle of 326.3 degrees, which is still between 0 and 2 pi, which is 0 degrees to 360 degrees. But this angle points into the fourth quadrant, but we want to use, therefore, a negative r to get us back into the second quadrant. So accompany this angle with negative radical 13. And here's a second representation of this point in polar coordinates. So another way we can do this, if I keep that negative angle in red, negative 33.7 degrees, that's an angle that points into the fourth quadrant. So I would need to use a negative radical 13 to place us back into the second quadrant. Or I can rotate from that angle clockwise another 180 degrees. So in other words, remove 180 from this negative 33.7. That gives me an angle of negative 213.7 degrees roughly. This angle does point into the second quadrant, so I would go out a positive radical 13 to find that location. Now we could keep this up forever and make infinitely many polar coordinate representations of this point. All right, next page. On this page, we introduce the idea of a polar curve by discussing a curve known as a Limaçon, which has one of the general forms. R is equal to a plus or minus b cosine theta, or r is equal to a plus or minus b sine theta. Given the Cartesian functions and graphs below, graph the corresponding polar Limaçons. Our first Cartesian function is y equals 2 plus cosine of x. We're going to use this graph to help us graph its polar version, r is equal to 2 plus cosine theta. Now, these functions can be considered to be identical, except with the difference of how we interpret the inputs and outputs. We can also use function notation in the Cartesian. We could call this f of x, which represents the y-coordinate. So you pick x, the independent variable, calculate, and you get an output variable called the dependent variable, which is y. The same thing can happen in polar equations. So 2 plus cosine theta could be thought of as f of theta, where theta is the input variable. You plug it in, calculate, and you get an output variable r. But then you plot the point r theta with a polar interpretation. Let's explore this using technology, and then we'll talk about how to get a general graph by hand. So here we have a graph of cosine of x, which we're going to shift up 2 units. And we have our rectangular equation, y is equal to 2 plus cosine of x. Let me hide this for a moment. Now, as x varies, we get different outputs, indicated by that blue point. In this case, all of our outputs are positive, because the vertical shift moved the wave entirely above the x-axis. And then the curve is simply the path that this point takes as x varies. Now we'll consider the polar function. As theta varies, we simply rotate around the polar space. So if r is a function of theta, so r may vary as theta varies, and so you can see that r, the distance between the blue point and the origin, is changing as theta changes. And then our polar curve is simply the path of that blue point. So when doing this by hand, it is good to look at the Cartesian graph and identify a few key points. 0, 3, pi halves 2, pi 1, 3 pi halves 2, and 2 pi 3. Let's focus on this lowest point. Now for polar coordinates, we want to interpret the first coordinate in our rectangular as theta, and the second one is r, which would give me the polar coordinates bracket r comma theta. Notice we put the r first when in polar coordinates, but in rectangular coordinates we're going to interpret the second coordinate as r. In our polar grid below, let's identify the critical angles. We have angle 0, pi halves pi to the left, 3 pi halves pointing down, and then 2 pi's back where 0 is. Now looking at the point 0, 3, 0 is the angle, 3 is the radius, placing our first polar point right here. Our next point is pi halves 2. So when theta is pi halves, the radius will have shrunk to 2, putting a polar point right here. And this blue portion of the rectangular curve corresponds to this blue portion of our polar curve. Whereas theta varied between 0 and pi halves, the radius shrunk from 3 to 2. And then when theta is pi, radius is 1, giving us this point in our polar curve, and this is the closest we'll ever get to the origin. This green portion of our rectangular graph corresponds to this green portion of our polar curve, where between angles pi halves and pi, the radius continued to shrink from 2 to 1. Now we have when theta is 3 pi halves, the radius has grown back up to 2, giving us this point in our polar curve. This pink portion of our rectangular curve corresponds to this pink portion of our polar curve, whereas theta varied from pi to 3 pi halves, the radius grew from 1 back up to 2. And then finally, let's look at when the angle was 2 pi, the r will be 3, putting us back at the same point that we started at. And this final portion, which I'll leave in black, corresponds to this black portion of our polar curve, whereas theta increased from 3 pi halves to 2 pi, the radius grew from 2 back up to 3. And then because this function is periodic, we would expect this same Limaçon to be redrawn as theta continued to increase past 2 pi. Now let's take a moment and show you how to do this with Desmos. Open up Desmos, click on the wrench, click on the polar curve, and make sure that you are in radian mode. And type in the polar function using r's and thetas. R equals 2 plus cosine, and then for theta, just type it in. I'll change its color to black, and the technology gives us a more accurate graph. Notice that theta defaults from 0 to 2 pi. You can change these to any values, and notice that if you want just the upper half of the Limaçon, you can go from 0 to pi. To animate this, use a slider. I'll use capital T to represent my theta that is changing. Let t be 0, and then let's put 0 as the lower limit of t, and 2 pi is the upper limit of t, and 0.01 is the step size. Now to show the rotating angle, I'm going to make a green ray. To do that, make a point where the first coordinate is lowercase t cosine of capital T, and the y-coordinate is lowercase t times sine of capital T. I'll keep the ray green, make it dashed, and then little t vary from 0 to 50. And then I'm going to put as an upper limit on theta this capital T, which will be my slider. For the slider, this allows us to see the rotating angle and to see how r is changing as a function of theta. And in this case, r was always positive, so the polar curve is always being drawn in the same direction as the angle. Okay, let's look at our middle example next. Let's do this by hand first. Looking at the rectangular equation, y equals 1 plus sine x, that's just the sine of x graph shifted up 1. Notice it wasn't shifted up enough to be strictly above the x-axis. We do have an x-intercept right here. Some key points: 0, 1, pi halves 2, pi 1, 3 pi halves 0, and back to 1 at 2 pi. We have the same important angles. So our first point is 0, 1. So when the angle is 0, the radius is 1, giving us this point in our polar graph. When the angle is pi halves, the radius has grown to 2, giving us this point. And this blue portion of our rectangular graph gives us this blue portion of our polar graph. Whereas the angle increased from 0 to pi halves, the radius grew from 1 to 2. When angle is pi, radius is back down to 1, giving us this point. This green portion of our rectangular graph corresponds to this green portion of a polar graph. As theta increased from pi halves to pi, the radius shrunk from 2 back down to 1. Now we have this point of interest where at angle 3 pi halves, the radius will have reached a value of 0, meaning that this pink portion of our rectangular graph will correspond to this pink portion of our polar graph, where between angles pi and 3 pi halves, the radius continued to shrink until they got to 0, meaning that we've reached the origin. Then as theta continues to increase from 3 pi halves to 2 pi, the radius grows from 0 back up to 1, giving us this black portion here in the fourth quadrant. All right, using technology, let's change our polar function to 1 plus sine theta, and then animate. Okay, our third example on this page, we have a cosine function whose amplitude has been doubled, then it was reflected around the x-axis, and then shifted up 1. Notice because we doubled the amplitude, the vertical shift up 1 wasn't enough to prevent having portions of the graph that are still below the x-axis. Let's identify some important points here in this graph. We have 0, negative 1, pi halves 1, pi 3, 3 pi halves 1, and 2 pi negative 1. It's also going to be very important for us to identify where this graph has x-intercepts. So visually here and here. It's not obvious from this graph where those are, so let's find them by hand. Take this function and change y to 0 and then solve for x. So we get 0 must be equal to 1 minus 2 cosine x. Add 2 cosine x to the other side, divide by 2. We get cosine of x must be a half. And on a window from 0 to 2 pi, this occurs twice. Use your unit circle to confirm that this will occur at pi thirds and 5 pi thirds. So our first x-intercept in this graph is pi thirds 0, and the second one is 5 pi thirds 0. Now all of these angles that are significant, I'm going to graph in our polar graph. We have angle 0, angle pi thirds, pi halves, pi, 3 pi halves, 5 pi thirds, and 2 pi. Now this first point, when the angle is 0, the radius must be negative 1, meaning that when we're at angle 0, we need to plot a negative r, which will be plotted in the opposite direction as 0, giving us a polar point right here. So as we rotate through this interval from 0 to pi thirds, the r's are negative, meaning that the graph will be in the opposite quadrant of this. So over in quadrant 3. Let me extend my pi thirds ray. As we rotate through this window of angles, 0 to pi thirds, we're actually going to be drawing over here in the third quadrant because r's are negative. In particular, the r will grow from negative 1 and then arrive at the origin by the time the angle is pi thirds. Now let's focus on this blue portion. As the angle increases from pi thirds to pi halves, the radius grows from 0 to 1, giving us this blue portion of the polar curve. Now let's do this green portion of our rectangular curve. As theta increases from pi halves to pi, so rotating through the second quadrant, we will wind up at the point pi 3, which is here. And the r will continue to grow from 1 to 3. Let's do this next portion in blue of our rectangular curve. As theta grows from pi to 3 pi halves, the r will shrink from 3 to 1, arriving at this point, giving us a curve something like this. Now let's focus on this next green portion of our rectangular. Theta will increase from 3 pi halves to 5 pi thirds, and r will shrink from 1 to 0. Now let's do this final portion in red. Let me take this ray and extend it into the second quadrant. As our angle varies from 5 pi thirds to 2 pi, because r is negative, we're actually going to be drawing over here in the second quadrant. And we'll wind up closing off that inner loop. Okay, let's confirm this one with technology. We change our function to 1 minus 2 cosine theta. And because this time we have some negative values of r, it'd be helpful to see a second ray representing the opposite direction of theta. So I'll copy this ray, let little t vary from negative 50 to 0, and change the color to red. Let me play this through once. Now let's go through portion by portion. As t varied from 0 to pi thirds, notice that the graph was being drawn along the red ray, not on the green ray. That's because r was negative for all of these thetas. But then we reach the origin when theta is pi thirds. As we continue to rotate, r will grow from 0 to 1 by the time we get to angle pi halves. And then by the time we get to angle pi, r continues to grow until we get to r3. And then through the third quadrant, r will shrink from 3 back down to 1. By the time we get to 5 pi thirds, r has reached 0 again. So we're back at the origin. And then for the rest of the rotation from 5 pi thirds to 2 pi, r will be negative, so the graph will be drawn along the red ray, closing off our inner loop. Now a few things about Limaçons. Notice that all the graphs have a symmetry. I encourage you to use technology to play around with these formulas for different positive choices of a and b, sometimes doing plus, sometimes doing minus, and sometimes using cosine, sometimes using sine, to explore the family of Limaçons. A couple things I want to point out. In our first case, this a value was 2 and the b value was 1. So this cosine wave had an amplitude of 1 but then was shifted up 2, meaning that the graph is entirely above the x-axis in rectangular coordinates, which means r will always be positive and polar, and so we wound up with a polar curve that never reached the origin. In this middle case, a was a 1 and so was b. When they match in magnitude, we wind up with a polar curve that manages to hit the origin only once, but never has negative r's. And in the third case, our a value is 1 and our b value is 2. In rectangular, this meant we had a change in amplitude of the wave, followed by a vertical shift that left some portions of the graph below the x-axis. That corresponds to a polar graph that's going to have some negative r's involved, creating this inner loop. Okay, let's move on to the next page. Now, a rose is another kind of polar curve that has the general form r is equal to a cosine n theta, or r is equal to a sine n theta. We'll assume a and n are both positive, and that n is a whole number. So our first example is just y equals sine x, which has this general form. A would be 1 and n would be 1. Its polar curve version is r equals sine theta. Key points are 0, 0, pi halves 1, pi 0, 3 pi halves negative 1, and 2 pi 0. Remember, the first coordinate in Cartesian we're interpreting as theta, and the second coordinate as r. Notice that for half of this interval, the outputs are positive, and for the other half, the outputs are negative. The first point 0, 0 indicates that when theta is 0, so is r, so that puts us at the origin. By the time theta gets to pi halves, the radius has grown to 1, giving us a polar curve that looks like this. And then between pi halves and pi, the radius decreases back to 0, giving us a polar curve in the second quadrant. Now between pi and 3 pi halves, as the angles rotate here through the third quadrant, the r's are negative, so they'll actually be drawn in this first quadrant. It turns out in this case, the graph will retrace itself in the first quadrant. And as theta increases from 3 pi halves to 2 pi, sweeping out the fourth quadrant, the r's are still negative, so we're going to get a polar curve being drawn over here in the second quadrant, which turns out will retrace the second quadrant portion of this graph. Furthermore, it turns out that this shape is a perfect circle, and it gets drawn twice. Let's look at this with technology. As theta increases through the first quadrant, our radius grows from 0 to 1. As theta increases through the second quadrant, the radius decreases from 1 back down to 0. Now, as the green ray sweeps through the third quadrant, the r's are negative, so the graph will be drawn on the red ray, and it winds up retracing itself. And then as the green rays sweep through the fourth quadrant, again, the r's are still negative, and the graph retraces itself again. From start to finish, the circle draws itself as theta varies from 0 to pi, and then redraws itself as theta continues to vary from pi to 2 pi. In this middle example, a is 1.5 and n is 2. This 1.5 will change the amplitude of the wave, and this 2 will change the frequency, or the period. The period is cut in half and the frequency is doubled. So now we get a wave completing itself in half the period, from 0 to pi. Some key points are 0, 1.5, pi fourths 0, pi halves negative 1.5, 3 pi fourths 0, pi 1.5, 5 pi fourths 0, 3 pi halves negative 1.5, 7 pi fourths 0, and 2 pi 1.5. The angles of significance in this graph will be shown here, every multiple of pi fourths basically. Let's focus on this first green portion. Between angles 0 and pi fourths, the radius begins at 1.5 and decreases to 0. So at angle 0, we have a radius of 1.5, and by the time we rotate to pi fourths, the radius shrinks to 0. Now let's focus on this red portion that's below the x-axis, so negative r's. As theta increases from pi fourths to pi halves, because r is negative, we're actually going to draw down here in the third quadrant, and the r decreases from 0 to negative 1.5, corresponding to this portion of a polar curve. Now continuing with this portion of the curve that's below the x-axis, as the angle rotates from pi halves to 3 pi fourths, r is still negative, so we're drawing over here in the fourth quadrant. We wind up closing up a loop. In fact, notice that this red portion of the graph that's below the x-axis corresponds to angles between pi fourths and 3 pi fourths. So as we sweep through this range of angles, we wind up drawing a loop on the opposite side of this range. This next portion of the curve is entirely above the x-axis, corresponding to angles between 3 pi fourths and 5 pi fourths. So that's this range of angles in our polar graph. And we're going to draw another loop, but because r is positive, this loop will be drawn in the same direction and will extend as far as 1.5 units away from the origin, giving us a complete green loop right there. Now this next portion of the Cartesian graph is entirely below the x-axis, so the r's will be negative. These are angles between 5 pi fourths and 7 pi fourths. As the angle sweeps through this portion of our polar grid, we'll actually be drawing a loop, but up here in the first and second quadrants. And that loop will extend as far as 1.5 units away from the origin. And then finally, this last portion here highlighted in green, as the angle varies from 7 pi fourths to 2 pi, the radius grows from 0 to 1.5. So that's sweeping out this portion. The radius is positive. We wind up closing this loop that we started at the beginning. These loops are also known as petals, and you can call this shape a 4-petal rose. Let's confirm with technology. I'll play through once. And now let's break it down. As theta increases from 0 to pi fourths, the r shrinks from 1 to 0 and is drawn on the green portion. As theta varies from pi fourths to pi halves, the r's are negative, so it's the red ray that's drawing the graph. As theta increases from pi halves to 3 pi fourths, we continue having negative r's, and we close off that loop. Now vary from 3 pi fourths through pi to 5 pi fourths. That gives us a loop that was drawn along the green ray. Now as the green ray varies from 5 pi fourths through 3 pi halves, the loop drawn was along the red ray. And then as we complete the rotation from 7 pi fourths to 2 pi, we close off that first loop. Let's use this thinking to help us with our third graph. In this case, our amplitude is 2, so the tips of the petals will reach as far as 2 units away from the origin, and our n is 3. This has the effect of tripling our frequency, which multiplies our period by 1/3. So we do a complete cycle from 0 to 2 pi thirds, and we do 3 such cycles between 0 and 2 pi. The angles I'm going to keep track of this time are only these angles that are the x-intercepts of our graph. So angle 0, pi thirds, 2 pi thirds, pi, 4 pi thirds, and 5 pi thirds. This first portion of the rectangular graph, highlighted in green, will give us a petal that's in the same direction as these angles from 0 to pi thirds. There will be some symmetry involved too, so the tip of the petal should be halfway through this rotation, and we get a complete green petal. The next portion of our rectangular graph, highlighted in red, is below, so we have negative r's. So as our theta continues to increase from pi thirds to 2 pi thirds, we're going to draw the same petal, but it'll be in the opposite side of these angles. And the tip of the petal will be 2 units away from the origin. Now as theta rotates from 2 pi thirds to pi, this portion of our rectangular graph will correspond to another petal drawn in the same direction as these angles. Now let's focus on this next portion, highlighted in red, of the rectangular graph. As the angles increase from pi to 4 pi thirds, we're going to draw a petal on the opposite side, which will retrace the green petal that's already there. Now let's rotate from 4 pi thirds to 5 pi thirds, corresponding to this portion of our rectangular graph, giving us a green petal in the same direction as these angles, so it will retrace the red petal that's already there. And then finally, as we complete the rotation from 5 pi thirds to 2 pi, that corresponds to this final red portion of our rectangular graph, giving us a petal opposite these angles, which will retrace this petal over here in the second quadrant. So in the end, we wind up drawing 6 petals, but 3 of them perfectly overlapped the first 3 that were drawn, and the entire image is actually produced in half of a rotation. Let's look at technology. I'll play through once. Notice we only have 3 visible petals, but it was drawn twice. As theta varied from 0 to pi thirds, we drew 1 petal. Then we drew a petal in the opposite sense. Then we drew a petal in the same sense. And by the time we got to pi, the drawing was done. And the second half of the rotation just redraws this 3-petal rose. So in summary of roses, in this first case, A was 1 and N was 1. You can think of this perfect circle here as a 1-petal rose that draws itself twice and extends as far as 1 unit away from the origin. The A indicates how far the tips of the petal will get from the origin. In the middle case, A was 1.5 and N was 2. We wound up creating petals that extended to 1.5 units away from the origin, and we drew a total of 4 petals with no overlap. It required a full rotation to draw all 4 petals. And in this third case, A was 2, which tells us how far the tips of the petals are from the origin, and N is 3. We only had 3 visible petals, although we could argue we drew 6 petals over the full rotation from 0 to 2 pi. But the second 3 petals were just repeats of the first 3 petals, so the entire graph was drawn as theta varied only from 0 to pi. It turns out that if n is odd, that we will see exactly n petals, or n loops, and to see all of the petals, you only need to let theta vary from 0 to pi. And if n is even with these roses, then there will be 2n visible petals, and you need theta to vary from 0 to 2 pi in order to see all of them. All right, let's go to the next page. The Cartesian graph of r against theta is given. Convert it to a polar graph. Notice our input variable is interpreted as theta, and our output variable is interpreted as r. That's similar to what we've been doing so far. Now we want to begin by identifying the angles of interest. We begin at angle 0, and then notice that r is constant up until angle 2 pi thirds. Then between angle 2 pi thirds and angle pi, the r decreases from 2 to 1. Then the r stays constant up until we are halfway between 4 pi thirds and 5 pi thirds. Add them together, divide by 2. This is 3 pi halves. There are two x-intercepts, which will be important, 5 pi thirds 0 and 2 pi 0. And then we have a minimum value of r occurring halfway between 5 pi thirds and 2 pi. So add those together, divide by 2. So 5 pi thirds plus 6 pi thirds is 11 pi thirds, divided by 2 is 11 pi sixths. I'm going to highlight all of these angles in my polar graph to the right. So angle 0, angle 2 pi thirds, angle pi, 3 pi halves, angle 5 pi thirds, 11 pi sixths, and then back to 2 pi. I'm going to focus first on this portion of our rectangular curve highlighted in orange. As theta varies from 0 to 2 pi thirds, so sweeping out this portion of our polar graph, the r remains a constant 2. Thus we get a portion of a circle being drawn as theta varies because the radius stays constant at 2. Next, let's do this green portion of the Cartesian graph where between 2 pi thirds and pi, so as we sweep out this portion of our polar grid, we expect the r to decrease from 2 down to 1, producing something like this. Now let's do this blue portion of the curve. As the angle sweeps from pi to 3 pi halves, the radius becomes constant again, constant 1. So again, portion of a circle. Okay, let's do this pink portion. Between angles 3 pi halves and 5 pi thirds, the radius quickly decreases from 1 down to 0. So as we sweep through this portion, the radius will quickly shrink to 0. Now let's focus on this red portion of our rectangular graph. As the angles vary between 5 pi thirds and 11 pi sixths, the r's are negative. It can be helpful to extend our 11 pi sixths ray through into the second quadrant. When theta is 11 pi sixths, the r is negative 1, placing us at this point right here. So the r will decrease from 0 to negative 1 as we rotate through these angles, which puts the graph over between these rays. And then finally, the last portion of our rectangular curve, which I'll highlight in red still to indicate negative r's. As the thetas themselves go from 11 pi sixths to 2 pi, our negative r's will go from negative 1 and then back to 0. So they'll be drawn in this portion of the second quadrant. If your graph looks too cluttered, you can erase all the rays so you can actually see the graph, or you can leave them in. Let's move on to the next page. Plot the polar curves below. So we have two special cases of what r equals a constant looks like, and then what theta equals a constant looks like as polar equations. If r is equal to a constant 3, that means that as theta increases, r stays 3. In other words, no matter what the angle is, the r should be 3. So when the angle is 0, we expect a point to be 3 units away from the origin. When theta is pi 6, we expect the same thing, 3 units away from the origin. In the end, we're going to get a bunch of points along a circle centered at the origin, radius 3. The second example is theta equals a constant, in particular theta equals pi thirds. So here's the trajectory pi thirds, and here's the opposite direction. So as long as theta is pi thirds, it doesn't matter what r is. So r could be 0, giving us a point at the origin. R could be a half. R could be 1, 1.5, 2, 2.5, 3, 3.1, etc. Or r could be negative, negative a half, negative 1, negative 1.5, negative 2, etc. So this will produce all points basically just along this line. So our graph winds up just being this line through the origin, where half of the graph goes in the direction of pi thirds, and the other half of the graph goes in the opposite direction of pi thirds. So this graph of theta equals pi thirds could also be represented by the graph of theta equals negative 2 pi thirds, or by the graph of theta equals 4 pi thirds. Theta equals any of these angles, and then many more are possible, would produce the same line. Let's go to the next page. Graph each Cartesian equation, then convert the equation to polar form. So here we have some just basic lines. Y equals 1/2 x. This is a line that passes through the origin and has a slope of 1/2. To find an equation for this line through the origin, we simply need to find any angle in standard position that terminates on that line. So this angle theta, that's acute and positive, will suffice. We can also go through the motions of converting my x and y coordinates. If you recall, x can be found by doing r cosine theta, and y can be found by doing r sine theta. If I substitute these into our equation y equals 1/2 x, we get r sine theta is equal to 1/2 r cosine theta. Let's assume r is not 0. If it is 0, then we'd simply be at the origin, which is already a point on this curve. So assuming r is not 0, we can divide it away, giving us an equation that's independent of r. Then we can divide by cosine. Sine over cosine's tangent. So whatever theta is, the tangent of theta would be 1/2. And then we can find theta by finding the inverse tangent of 1/2. In radians, that would be, using a calculator, approximately 0.464 radians, or in degrees, approximately 26.6 degrees. So this would be our equation. Theta is equal to arctangent of 1/2. Remember, if theta is equal to a constant, we get a line through the origin. Now how about this next line? This line has a y-intercept of -1 and a slope of 1/2. It does not go through the origin. So we have the rectangular equation. Change y to r sine theta and x to r cosine theta. This time I cannot divide the r's away because I would have to divide this 1 by r as well. So the r's do not cancel. I will go ahead and double both sides of the equation to get rid of the fraction, giving us 2r sine theta is equal to r cosine theta minus 2. This is an equation that we want to solve for r and put it in terms as a function of theta. So I'm going to subtract the r cosine from right to left side, factor out the r, and then divide. This is my polar function that will make this line. R is equal to -2 over 2 sine theta minus cosine theta. Let's confirm this one with technology. Okay, I've typed in our equation. We have the green ray and the red ray, and let's play. As t varies, we get different values of r, creating points that appear to follow a line. Switching to a rectangular grid and playing again, it appears the entire line was also drawn as the angle varied from 0 and pi. So by the time the green ray completes half of a rotation, we've drawn the entire line. And we redraw it as t does the second half of the rotation. Okay, this concludes our lesson on polar coordinates and curves.